Organometallics are such entities in which we are having a carbon bonded with a metal. Now, keeping in mind on the basis of organometallics, we can classify them into two categories. If an organometallic metal is lithium or magnesium bonded with alkyl group, so this is RMgX, commonly called Grignard reagent. So RMgX is a Grignard reagent, commonly called. So if we are reacting organolithium or organomagnesium metal. So organolithium or organomagnesium, once they are being used, you see we have a same substrate. If it is reacted with this, it always undergo direct addition, one to addition, no conjugate addition. But let's see if we are using other kind of metals, if we are using some other system, other type of metal, let's say this metal may be cuprous, it may be cupric, it may be zinc, it may be palladium, tin, ruthenium, rhodium, titanium, or any other metal, but not lithium, not magnesium. If it is any other D metal, F metal, P metal, S metal, but not lithium or magnesium, it shall always undergo conjugate addition. You see this alkyl group present here is transferred to beta position here. It is a conjugate addition, but this is a direct addition. So organolithium and organomagnesium always undergo direct addition, whereas all other organometallics in which metal is not lithium, not magnesium, but any other metal, S, P, D, F metal, any one, they shall always undergo a conjugate addition. So this is a summary of the factors that are important in this case. The last slide that I am interested to present is the addition to triple bonds. So this was the all over. You have come across 4 different aspects: electrophilic addition to olefins, similarly electrophilic addition to nucleophilic addition to carbonyls. Now we can revert the reactivity of these substrates so that the carbonyl can be electron deficient, can be converted into electron rich, and carbon olefinic carbon, which is electron rich, can be converted into electron deficient. This is what we have seen today. So all 4 types of additions we have covered up. But that was addition to olefin or addition to carbon oxygen double bond. But now we are focusing on the addition to alkynes, carbon carbon triple bond. Keeping in mind there is no versatility in addition to alkynes, except a few things. Let's see, when we are discussing, we have this alkyne. You see, if we are adding hydrogen to this, first one hydrogen molecule shall add one hydrogen to this and one to the other end. Second hydrogen, one hydrogen going to add this side, other hydrogen going to add other side. First, it shall generate this olefin, right? Hydrogenation is always a thin addition, because so both hydrogen shall be added to same side like this one. It shall be further hydrogenated to this one. So there is no versatility. Similarly, we add halogen. Both halogen shall add to this one. Again, resulting two high halogens this side. Again, 2 halogens shall be added. We shall have 4 halogens present on adjacent positions. Again, there is no selectivity. But what is important of 2 reactions I am going to present, which gives a little selectivity in addition to alkynes, carbon-carbon triple bond. Carbon-carbon triple bond, if we are interested to stop this reaction here, if we are using hydrogen, molecular hydrogen, palladium we are using as catalyst, which is adsorbed on charcoal, then it gives you always this type of fully saturated olefin, fully saturated hydrocarbon, no double bond. If we are interested in the bond formation like this, cis bond or a second bond. These are formed, but it forms and then converts into this. But if we are interested to stop the reaction here, then we can do it. We can do the hydrogenation over palladium, but palladium should be poisoned, mean its activity of catalyst should be decreased. So this is called Lindner's catalyst, in which we poison this with lead. Palladium and lead alloy is used. Palladium is very active, very expensive as well. Lead is not expensive, and lead and palladium are when mixed with each other, it forms an alloy. That alloy is when used, it is not much activated. It stops, it reduces the triple bond like this into this one. This is syn addition, both hydrogen adding from same site. You see, cis olefin is formed. But this catalyst is not able to reduce the cis olefin into saturated hydrocarbons. This is a drawback. So which drawback is useful for us? So triple bond adds to form cis olefin. This is a very clear simple addition. You have already come across the mechanism. Single step hydrogenation, always syn addition. So this is simple syn addition, nothing else. But if we are interested in a trans olefin, we cannot perform this. But if we are interested, then it can be done with lithium in liquid ammonia. This has been observed when we are doing this. It results in the formation of a trans olefin rather a cis olefin. So what is going on in this case? The mechanism I have presented below. What happens in this case? Just focus here, carbon-carbon triple bond. So both pi bonds are not going to react. You see, there is a double bond. So one pi bond is reacting. So pi bond contain how many electrons? Two electrons. What happens? In this case, lithium is a metal. Do not forget. This is done in liquid ammonia. So temperature should be minus 78 degrees Celsius. If this temperature is increased, so ammonia shall evaporate. Ammonia has a minus 54. It has a boiling point. So anyhow, this temperature should be minus 78 to maintain ammonia in liquid state. What happens? Lithium loses one electron. Where this electron goes? You see, we have a pi bond, but pi star is empty. So this electron goes to pi star. If this electron goes to pi star, what happens? The three electrons are present in system. Two are in bonding, one in anti-bonding. So what is the bond order? 2 minus 1 divided by 2, which is equal to half. Bond order is decreased to 1. So this bond, one of the pi bond shall break. When it is broken, so we have just double bond remaining. We have carbon-carbon double bond. Now we have three electrons present. One carbon shall have two electrons, other can have one. It is impossible. One have one and a half, other have also one and a half. This is impossible. Electron cannot be further divided. So one shall have two electrons, other shall have one electron. So this is the orbital I have presented. One orbital is having one electron, other is having two electrons. If it is having two electrons, both shall have opposite spin. If it has one electron, it can have any spin. So it is just like a negative charge. It is just like a radical. This is what we call what is being generated. This is a radical anion. Now you can argue why they are opposite to each other. Maybe this orbital and this orbital are opposite to each other. This carbon, this bond can be other side, and these two orbitals on the same side. If they are on same side, they are eclipsing each other. Lone pair repel each other, if you remember, as per lone pair repulsion theories. Lone pair has highly repulsive forces. Due to this reason, it shall not be a stable conformation. That's why they are opposite. These two must be opposite to each other. What happens next? Ammonia is a source of proton. This negative charge takes a proton from ammonia, converts that into amide, NH2 negative. So it has been protonated. So we get a hydrogen at this place. This hydrogen is coming from ammonia. That's why I have presented it in blue color, showing that this hydrogen is coming from ammonia. Now we get a free radical. This free radical again undergo gains an electron. Lithium goes to lithium plus. It loses one electron. This one electron adds to this orbital. When it adds to this, we again get two electrons here. Two electrons very similar, paired up. So it is just like an equivalent of carbonyl, resulting in this one. So this entity further undergo very similar action you have come across here. Ammonium shall provide a proton to this, and they shall be adding. Both hydrogens are added from ammonia, that which we are using as a solvent. So what is happening? Both hydrogens are added opposite to each other, resulting in the formation of this trans solvent. So we can control the olefin addition, hydrogenation to olefin, alkyne in syn addition, and we can carry out the enzyme hydrogens, but conditions are, reagents are entirely different. This is a unique feature that is only reportable or under discussion we can bring into consideration addition to triple bonds. Otherwise, all other additions are very similar to carbon-carbon double bond addition. So just like I have to first double bond reacts to form an olefin, which shall be always a syn addition. If halogen is adding, the addition of halogen is again very simple. Two halogens shall be added in opposite way. Keeping in mind, it shall not be syn addition. Both bromines are not going to act the same way. Both bromines are adding very similar following two steps mechanism that you have already come across. So second, two bromines are added. Again, two bromines shall be added. We shall have two bromine on this carbon, two bromine on this carbon. Similarly, for oxidation, everything is very similar. It shall not stop to this level. It shall stop to this saturated level. In fact, this is a unique feature in alkynes. Only one selectivity, two selectivities are there that I have highlighted in this case. Right, so this is a suggested reading, chapter number, I think I haven't changed this. This is the same that I have suggested in previous lecture. So I shall get this change in next lecture. So this is the end of additions. Now we shall focus on substitution reaction in next lecture. Substitution, replacement of one entity by the other. This was, it is the end of such courses, different series of lecture that we focus only on addition. You have come across addition across carbon-carbon double bond, and today you have come across to carbon-carbon triple bond. You have also come across addition to carbon-oxygen double bond. So these three different type of substrates you have come across. So olefins are electron rich, always react with electrophile. Carbonyl, electron deficient, shall always react with nucleophile, but we can invert their reactivity. You have seen how we can invert that. Enolates shall revert the reactivity of carbonyls, and the presence of a electron withdrawing by resonance mean minus R group attached to olefinic system shall make it electron deficient. So we can revert the reactivity of them as well. So our topic, we shall focus on substitution reaction starting from tomorrow. You can ask any question if anything is unclear.
Excuse me, sir.
Ji?
Sir, in esters, the alkoxy group attached to carbonyl carbon is no doubt electron donating with respect to resonance, but it is electron withdrawing inductively. Then why it prefers conjugate addition?
Which you are talking about?
I'm
Which
talking
slide?
about, sir, esters. Comparison,
Anji.
sir, previous, yes, sir.
What is your question?
Sir, I'm saying that in esters, that alkoxy group, methoxy group, attached with carbonyl carbon.
Yeah.
Sir, it is electron donating with respect to resonance but electron withdrawing inductively. Then why it
And
prefers conjugate addition?
electronegativity of chlorine is also quite closer to oxygen, right? Not very
Yes.
big difference. If oxygen is 3.47, this is 3.3 approximately, very close in reactivity. But here is the electron donation. Chlorides has much steric hindrance because three
Yes.
lone pairs are there. So it has a competition which lone pair should be donated. As a result, due to this competition, it donates rarely. That's why there is a poor increase in electronic density around this carbon. If you are comparing it with oxygen, it has almost same electronegativity but two non-bonding electron pair. So it has a less contribution. More contribution than halogens. So two non-bonding electron pair shall have a less competition. As a result, it shall increase more electronic density around this carbon. All right. So making this carbon less electropositive. If this is nitrogen is having only one non-bonding electron pair, so it is donating electron density more higher. As a result, it is decreasing the electrophilicity of this carbon. So this carbon shall become more electrophilic. This is the comparison in fact.
सर
Any other
कीटोन
question?
सर कीटोन्स में तो आपने कहा मिथाइल ग्रुप अटैच्ड है तो इलेक्ट्रॉन डोनेटिंग इफेक्ट आएगा जिसकी वजह से वो जो चार्ज है वो इतना ज्यादा नहीं प्रोड्यूस होगा तो सर यहाँ पर मिथॉक्सी ग्रुप है सर ये भी तो इंडक्टिवली इलेक्ट्रॉन विदड्रॉइंग है तो सर यहाँ पे भी तो थोड़ा सा डेफिशिएंसी क्रिएट होगी नहीं
Resonance effect always dominate over the inductive effect. You have already come across this.
ओके सर
You have already seen this before in basic concepts to the organic chemistry in previous semester. Whenever you are having the two factors are applicable, one is mesomeric, other is inductive. Mesomeric factor always dominate over inductive. So when the two factor you are comparing, both are operative, then inductive effect shall not operate. It shall not dominate. All right. So mesomeric factor always dominate. So we have less than 1 minute if there is any other question.
थैंक यू सर